The purpose of this video is to introduce the independent samples t-test, which corresponds to Chapter 11 in your textbook. The independent samples t-test is used to compare two means in a between groups design. That means that each participant is in only one condition. And of course, since we're comparing two means, there's only two possible conditions. So those are the circumstances under which we use the independent samples t-test. A major difference between the independent samples t-test and the paired samples t-test is that we now have a new comparison distribution. It's the distribution of differences between means. So this is different than how we computed the set of scores that we used from a paired samples t-test. Because if you remember in the paired samples t-test, we had a set of scores, and for each pair we subtracted one from the other and created a set of different scores. What we do in the independent samples t-test is kind of the opposite. We create a mean for the first group and then a mean for the second group, and then we take the difference between means. And that's how we get this name here, where we say differences between means, because we are in effect calculating the means first and then the differences second, which is different from that distribution of mean differences, right? Because we're taking the average of a set of different scores, mean differences. There's a lot of differences that we talk about when we're talking about what kinds of distributions we're using, so I know that that can be kind of confusing. But you'll notice too that the scores tend to pile up around 0. That the mean in the population, if the null hypothesis is true, is that the mean of the first population is equivalent to the mean of the second population. So that if you had mean 1 equal to mean 2, then we would say mu sub 1 minus mu sub 2 equals, well, since they're the same, you could say mu sub 1 minus mu sub 1, which gives you 0. So in the population, the difference between mu sub 1 and mu sub 2 is 0. This will be important later on. Okay, so just to kind of rewind a little bit, let's talk about the hypothesis tests and their distributions. Now remember that we can talk about the z-test, and that has a single sample, right, because we're comparing it to a population mean, and it is has a comparison distribution of the distribution of means. And the difference between that and the single sample t-test is that for z, we know sigma, but for t, we estimate it. So that's the main difference between these two. For the paired samples t-test, again, like I said, we're talking about a distribution of mean difference scores. So we get a set of different scores and then we take the mean. Well, whereas here we get a mean of sample 1 and we subtract the mean of sample 2, and that's why we have a distribution of differences between means. You'll see that the same 6 steps of hypothesis testing are used here. We identify the populations, distribution, and assumptions. We've already talked about the distribution as being a distribution of differences between means. We know that the two populations correspond to our two different samples, our manipulation of the independent variable. And we'll talk a little bit about those assumptions, which they're basically the same as what we've been assuming all along. But we'll get to that as well. Stating null and research hypotheses, getting the characteristics of the comparison distribution, what are our critical values, what's the test statistic, and then we make a decision, as we've been doing all along. So here's an example. In the first step for a particular problem where what we're doing is we're trying to tell how people rate wine that they're drinking if they believe they're drinking from a $10 bottle versus how they rate it if they believe they're drinking from a $90 bottle. And in actuality, they're all drinking the same wine. So population is one is people who are told they're drinking the $10 bottle, and population 2 is people who are told they're drinking wine from a $90 bottle. The distribution is a distribution of differences between means. And our assumptions. Participants were not randomly selected here, so we need to be cautious with respect to generalizing. We don't know whether the population is normally distributed, and our sample size is kind of small. We haven't gotten to that yet. I'll show you in a minute. And the other is our dependent variable, our scale is scale. Okay. So now we state the null and research hypotheses. The null hypothesis is, on average, people drinking wine they were told from a $10 bottle give it the same rating as people drinking wine they were told was from a $90 bottle. So we're hypothesizing here that mu sub 1 is equivalent to mu sub 2. Our research hypothesis, in contrast, is that on average, people drinking wine they were told was from a $10 bottle give it a different rating than people drinking wine they were told was from a $90 bottle. So again, we have a non-equivalence here. So what does that tell us about what kind of tails we're going to have in our test? Think about that for a minute, and maybe pause it if you need to. Okay, so here what we've got is a two-tailed test. So that's what our hypotheses reflect, is a two-tailed test. All right, in order to determine the characteristics of the comparison distribution, this is one of the big changes. Okay, before we just had to estimate the standard error, and it was based on an estimation from a single set of scores. But now we kind of have to figure out what the variability is for one sample and what it is for the other sample and combine them in some way. And the amount of information that we get in each sample, so the number of scores in each sample, gives them a different weight. So you'll see that we have in the y variable here, n equals 5. And in the x variable here, n equals 4. So because what you guys know about sample size is that it's a better estimate. The more people we have, the better the estimate. And if we're more confident about a particular estimate that we have, we want to give it more weight. So you'll see where I'm going with this in a minute. So here you'll start to notice too that we have now another subscript. So the variance for all of the x scores. So that's our first sample. And here we have the variance for all of the y scores. And all you need to do is calculate the estimated standard deviation just like you have been, just for the set of scores for the group that's x and for the set of scores that's the group for y. So we have one more piece of one more thing we need to do in order to get a single estimate of the standard deviation. And that estimate of the standard deviation in a one sample t-test is called the pooled variance. And I want to also point out that we are using variances until the very end of this step when we get the standard error. So be careful not to take the square root until the very end. Remember that we're working with variances and we're making a pooled variance. So the first step in finding this standard deviation, because that's the first part, remember we've done this for every single t-test we've done so far, figured out what the standard deviation is in the population. We have to get the variance for each sample, so that's first. And the second part is we have to pool the variance. And remember I said we want to give more weight to something that has more information. So in this case, you'll see that we actually are going to give more weight to the y sample because the n is 5. And the number of degrees of freedom for y is going to be equal to the number of participants in the y group minus 1. So in this case, it's going to be 4. The degrees of freedom x is going to be n sub x minus 1. And in this case, we had an n of x for 4, so we have 4 minus 1 equals 3. The total degrees of freedom is the sum of the degrees of freedom x plus the degrees of freedom y, or if you did all the math, you could say capital N, which is the total number of participants, minus 2. Okay, so in our case here, we have a degrees of freedom total of 4 for degrees of freedom y plus 3 for degrees of freedom x gives us 7. So we're going to actually weight this so that it's 3/7 variance of x and 4/7 variance of y. If we had equal sample sizes, we would evenly weight each of these measures of variability. So that's how we're going to get the pooled variance, which is our equivalent of the standard deviation in the population. So the next part is getting the standard error, which is again what we've been doing all along. So we're going to convert the pooled variance to squared standard error. And in order to do that, we take the pooled variance for x and we divide by the number of participants in the x sample. So we take the pooled variance and we divide it by, in our case, 4. And for the variance for the squared standard error here, we would divide it by 5. And this is analogous, okay, if we took the square root of this whole thing, right, if we said s squared pooled and divided by n, and we took the square root of the whole thing, we could actually say s pooled over the square root of n. And this should look familiar. That's the standard error, right? So that's why this is s squared pooled. It's the variance divided by n. So now we're going to add these two variances together to get an estimate of the variance of the distribution of differences between means. So this is how we get the variance. And then all we have to do is take this value and take the square root, and that will give us S sub difference, which is our standard error. Standard error of the distribution of differences between means. So the other thing you could say is, oh yeah, S sub difference equals the square root of S squared sub mx plus S squared sub my. So you could combine these last two steps if you wanted to. So now we have our standard error. This is one of the things I think people find the hardest, is going to find the pooled standard or pooled variance and then finding this standard error. So then we get to step 5, and these two end up being equivalent. And the reason they're equivalent is because, remember I said if you expect your mu sub x to be equivalent to mu sub y, then if you take the difference of those two, it would be like saying mu sub x minus mu sub x equals 0. So if we just said that was 0, then we could really reduce it to this. So the mean of our x's minus the mean of the y's divided by the standard error of the difference. So we find our critical values, and now we're going to base this on our degrees of freedom, which is n minus 2, in this case 7. And here's our critical values. It's a two-tailed test. And we calculate the test statistic, which we find to be negative 2.44. I know I didn't go through all the details of how you get that because the next video gives you the whole 6 steps of hypothesis testing. So if you want to report your statistic, you put the degrees of freedom here, your calculated t, and then it's less than 0.05.